Hello, sir. This is our project review for cybersecurity. I am Sundar Kanan, 17BCB0103.
Hello, sir. This is P. Sai Shashank, 17BC0283.
This is Charashma, 17BC2161.
Hello, sir. This is Sudeep Singh, 17BC0356. So here we have built a multi-user chat system, which is an application through which the client can speak with different clients associated in a same network area, that is LAN. The communication between different clients is finished utilizing client-server models. To verify the communication between the client and server, RSA encryption is being used. The verified chat framework is intended to give security, confidentiality, and integrity of communication between people involved by using the underlying technologies of RSA algorithm, digital signature. As its method of authentication and verification of users, the user can easily transfer the messages. The socket program utilizes the client attachment and server attachment techniques to interface the local host to the name, host, and port. The communication between different clients is finished utilizing client-server model. Next.
So now I'll talk about the proposed framework of our project. So basically the first part is creating a basic chat server where we have a client and server set up and ready. Then the server should recognize that the different user clients are being added, and the client sends all its respective keys to the server so that it's stored in the server. This way, a client is being added to the chat system. The next part will basically be sending direct messages. So we send the messages from the client to the server, and the server allocates the messages to all the other clients present on the network. So this is basically the chat API which we have created. Then the algorithm which we use to encrypt the messages is the RSA algorithm and RSA encryption algorithm. And the prime numbers are quantum random prime numbers, which is a very important aspect in our project, which makes the security of the algorithm much more higher as compared to a normal random number generation, which is pseudo random numbers. Then we have various encryption and decryption functions which are present in our project. And we are also hashing the encrypted values from the client or the server and passing it to the other places respectively, so that the confidentiality of the message is protected during the passage of the message. We're verifying this using a digital signature at the client end or at the server end. Start.
So we're basically going to use a chat system where there are two clients or two or more clients. So for the passing of messages from one client to the other, we'll be following the TCP/IP protocol. So the TCP/IP protocol is basically the transmission control protocol and the internet protocol. This provides end-to-end data communication, specifying how data should be packetized, addressed, transmitted, routed, and received. This functionality is organized into 4 abstraction layers, which classify all the related protocols. So the technical standards underlying this internet protocol is the constituent protocols of the IETF. So basically, it ensures secure transmissions from one client to the other.
Okay, so now let's talk about the RSA encryption algorithm. So Rivesh Shamer Alman is one of the first public key crypto systems which was developed at that time. So the RSA algorithm works this way. So we have 2 prime numbers P and Q, and we are finding N, which is P into Q, and we find phi of N, which is nothing but P minus 1 and Q minus 1. We find E, which is nothing but E is a number such that it is a co-prime number. It's a co-prime with phi of N. And now our public keys which are available to us is basically N and E, which we have. So the public key basically, which is generated in RSA, is sent to all the clients, all the clients know this public key. So the algorithm works in such a way that if we are sending a message from A to B, A encrypts a message using B's public key, which is available, and sends it to B. Once it's sent to B, B basically decrypts the message using its own private key. And this is how RSA algorithm basically works. So that's how we have shown the public key, which is N and E here, and the private key, which is D here. So the encryption and decryption basic formulas have been displayed here. So now let's talk about something called as quantum random numbers. So this is the highlight of our project, and we'll talk about it in detail here. So quantum random numbers are random numbers which are generated not by using any machine algorithms which are implemented, but using a specific quantum machine which is available to us. So these numbers which are generated are actual random numbers and not pseudo random numbers which are generated by a system. The pseudo-random numbers which are generated by the system are based on an algorithm and can be easily traced back and detected. But whereas quantum random numbers are, have their underlying source of, the purest form of random numbers which are available, and finding out these random numbers will be close to impossible for any user. So that's why our algorithm uses the quantum random number generator from IBM, which we have obtained, which is an IBM obtained gives an API to us, which generates quantum random numbers. And these random numbers are being used in our RSA encryption algorithm to make it 1,000 times secure as compared to the normal RSA algorithm. Okay.
So we'll be using socket programming in our project. Socket programming is generally a method for associating two hubs or two clients on a system to speak with one another. Well, one socket, or which is also known as node, tunes into a specific IP port, while the other attachment contacts the other frame connection. Server frames the listener socket while client connects with the server. So we have implemented the socket programming in Python to use TCP/IP protocol. This is the proposed architecture for our project. You can see it over here. There's client 1, and there's client 2, and there's server. So we'll be using RSA algorithm in our project. So how an RSA algorithm actually works is, suppose if there's a client A and client B. Each client has their own public and private key. So if client A wants to send a message to client B, the client A encrypts the message using client 2's public key or client B's public key, and then it sends the message. And when B receives the message, client B is going to decrypt the message using client B's private key. So we are following this in our project, and this is the proposed architecture. There's client 1, there's client 2, but the addition to it is the server. So the server over here has public keys and local addresses of all the clients present, and it also has its own public keys. So let us take an example over here. Suppose if client 1 wants to send a message to client 2, the message has to pass to the server. So the way it takes place is client 1 uses server's public key and encrypts the message, and then it sends it to the server. And then server uses client 2's public key and then encrypts the message and sends it to client 2. So server acts like a mediator over here between client 1 and client 2. So along with this, I would like to add on that we are using SHA 512 algorithm for more encryption and to make sure that the message is not corrupted. So the way this works is, this is basically a hashing algorithm. So client 1, when he wants to send a message to client 2, he sends the message along with the hash value, the computed hash value, to server. So server again computes the hash value and check if the hash value received by client 1 is same as the hash value calculated by server. If both of the hash values are matching, server sends the message to client 2. Else it does not send it. It just dumps it. So this entire process is known as digital signature process. Pause.
So now we're going to see the implementation part. So right now we're checking the code for the client side. So initially we are going to use RSA to encrypt using the server's public key. So the client 1 is going to decrypt using the client's private key. So finally, once we have encrypted the paths, in the end we're going to generate keys. Now the client, once it's receiving the public key from the server, client will send its public key to the server. So basically the client is going to receive the server's public key and send its own public key to the server. Now we are using hash SHA-512 encryption to make it more secure. Now finally the message which is being received from the server is decoded and hashed and then matched by the client. If it is matched, we decrypt the message from the server. Every time we register a new client to the server, we are gonna use a particular text called alias followed by the character sequence. That's the syntax to be registering a new client to the server. Now, if the client sends a message message to the server, it is encrypted, hashed, and finally sent to the server. And that is the code which is being shown right now. Next, we're going to talk about the RSA part of the code, which will be shown by my team member.
Okay, so now let's look into the RSA file. So what we have here. So this is the important package which is talking about. It is QRNG for generating the random numbers from the IBM server. We have set the provider. We're using the default QASM simulator, which is available from IBM for free. So that is what we have set here, and we set the backend as the IBM server to generate the quantum random numbers. Now these are helper functions for the RSA encryption. This is the coprime function which helps in finding the coprime of a given number, which we'll be using in our public key. Then this is a mod inverse function again to calculate the mod inverse. All these are mostly helper functions which are being used for our RSA. Then we have a modulo function which helps in calculating the modulo of the values. A YOLO totient function which we require to calculate the phi of n value. Then now let's come to the random number generation part, which is a very important part in our RSA code. So here we're generating a 32-bit random number, which is a very it's a 10-digit random number which we generate. We are dividing the number by 10 power 7 because we have tried using this algorithm with a 7-digit, 8-digit, 10-digit random number. But the problem is it takes a very long time. It takes almost half an hour to 1 hour for us to generate it takes like 15-20 minutes to generate the keys, and half an hour to 1 hour to send the message, to send the keys itself to the server by hashing it. So for ease of process and to just show you the demonstration, we have divided the random number so generated by 10 power 7 so that the encryption process can be handled smoothly. Now, for a more secure system, we can definitely leave it as a 32-bit random number. It will definitely take a lot of time, but the message will be sent very securely and it cannot be tampered with. So this is where we are simply another function which helps in finding out whether the random number generated is a prime number or not, and it keeps generating a number until and unless we find a prime number. So this is like a very, very, very good method to find a random prime number, because the prime number so obtained will be very random and it cannot be generated again. So this is the very important part of the project, and this is the quantum random number generator. Once this is done, these are again helper functions which help in finding the prime factors of the number and decrypt. Now we don't have separate function for decryption and encryption because both of them follow the same process. So we have a function called as decrypt which performs the same operation for both. Once this is done, we are again converting all our strings so obtained, characters so obtained into ASCII, so that they can be sent easily and can be decoded and sent easily across the client or server. Once this is done, we have the key generation part, which basically helps in generating the keys. We generate 2 prime numbers, and we perform all the RSA functions, find the YOLO totient function and all of that, and we generate the key basically and return it here. Once this is done, this is a basic test function which we have tried out to see if our RSA works, and that's about it. So this is where our RSA function ends, and we have generated the public keys and private keys for our client or server.
So this is the server.py file which we have implemented in our project. You can see there are few imports being used, that is socket, RSA, hashlib. And then these are the functions we defined over here, that is the encryption and decryption functions. So as we go down, we can see the establishment of connection between the server and clients. So initially the server has to get connected to the client. So in order to establish these connections, the client sends the name of the client along with the caret symbol to the server. So when the connection is established, the client changes his name, he updates his name. So then the server checks the data over here of whatever the client sent. And then the client receives the public key of the server, because we are using RSA algorithm over here, and client A has to encrypt the message using server's public key. So the server sends its public key to the client when the connection is established. So after this, the client uses the public key of server and sends the message, the encrypted message along with the hash value to the server. So then later again, the server computes the hash value, and if it checks if the hash value is same or not. If the hash value is same, it sends it starts the next process. If it is not same, you can see over here that there's a print function saying hash does not match, and it continues. It just dumps the code, the message, sorry. So coming to the decryption part, so now the server stores all the public keys of the remaining clients. Or if we talk about a one-to-one connection, the server should have the public key of client B, because in order to encrypt the message. So the same process follows as client A to server, that is server encrypts the message again and computes a hash value using the client B's public key, and then it sends the message to the public key. It sends the message to the server client B.
Okay, so we'll have a small demonstration of how project works. So here, let's start with the server here, and we can see that the keys are being generated for the server as well. And once that is done, I've generated a client here. Let me name it, say, ABC. Okay, so ABC is connected, and I'll send a message, say, hi, ABC. So this process will take a bit long because of the large numbers which we've used. And this is one message which is being sent to the server now. Parallel, let me start another command prompt where I'll start another client. Okay, so now we've seen that the key has been sent to the server and one client has established this connection. Now we come to the client side, we can see that the new client has been added, and along with the address of the client as well as the key. Let's start another client here. Okay. One is ABC and one is XYZ here. They've all connected. Now let's try sending a message and it should be able to go to ABC, I guess. Now we're seeing here that the server has sent a message and it's verified the message from XYZ is verified, and it's also sent the message to ABC. So this is what has happened. XYZ's message has already been sent to ABC. So let's try sending message from ABC to XYZ and see if the message has already been received. Hi XYZ. And yes, so the message from XYZ has been received by us here, and it's hi all. Verified, yes, it's hi all here. Now let's see if ABC's message has been sent to XYZ. Hi ABC. Yeah, it is. So ABC's message also has been received. So we spoke about a multi-chat user system, right? So let's go for another one, a third user, and try to do the same. CD there. Let's say Python client.py. Okay. Let's name this user DEF. Okay, and let me say that the message is hi everybody. He has been sent, the new client has been added, as you can see down here, the new client has been added and everything is ready now. Now, the hash is verified from DEF, the message is sent to ABC and XYZ, and all the messages have been sent to all the users. Now let's see if DEF's hi everybody message has been received by both the clients here. So let's say XYZ is sending another message saying, my name is XYZ. So let's see if the hi everybody message, yes, hi everybody message has been received from DEF to XYZ. Now ABC must be able to receive two messages. One is my name is XYZ as well as hi everybody from both the places. So let's see if ABC receives it. So ABC says, hi there, I'm ABC. So first message is hi ABC from XYZ, and the second message is hi everybody from DEF. So this way we can see that our chat system is able to send the messages to all the users and acts like a broadcast. The server basically helps in sending the message. So client sends the message to the server and server sends the message to all the clients present on our system. So this is how our multi-chat user system works.
So these are the screenshots of the results which we have obtained. So the screenshot is basically server after two clients have been connected and the keys have been shared. So the other one is the client one has been connected and the key has been exchanged, and the initial message is also being sent. So then over here you can see client 3 has been connected and the key has been exchanged, and client 3 has also received the first message sent by client 2. You can see the messages over here. And the other one is server after 3 clients have been connected and the keys are shared. So you can see that client has been connected. You can see the key and the key is stored over here.
This system is slow as compared to the other encryption method used, and the reason is because our system is 1,000 times more secured as compared to the other algorithms. So if you want to send the message extremely secured, then we can use the system, but use this system, but it takes a lot of time to send the message because the runtime, the prime numbers generated here are huge.
So to basically summarize the whole project, we have created a secure multi-user chat system, which was initially achieved by generating a quantum random prime numbers for encryption. So this is the most important aspect of our project, where the numbers which are generated randomly are almost impossible to recognize. So along with using the RSA algorithm for encryption and decryption of the message using the server's public key and private key and the client's public key and private key, the authenticity of the message was verified using RSA-based signature. So now the system implements a very secure system, and thus the computational overhead of the system is high.
Let's just finish up with the future enhancements which we can do on a project. So I think the speed is one of the major drawbacks of a project because the system being very secure and the numbers being very big. So the encryption, decryption as well as the hashing process takes very long time. So our system can be, the speed of the system can be improved using better infrastructure or better hardware. The other thing is the quantum numbers generated right now are 32-bit numbers. We can therefore generate 64-bit numbers as well, which are available online right now. So those will make the system even more secure, but will bring the drawback of making the system even more slower. And the last thing is we have made a very small, command prompt interface where we haven't had a big we don't have a big GUI interface where we can chat. So another extension of this project can be a proper GUI extension and make it a online chatting app. So this was a project, cybersecurity project review. Thank you so much. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.